Hi, my name is Amy. PyDSL for Python subset for better MLIR programming experience is part 2 of the talk. On the right, you can see an example of a PyDSL program where the loops are tagged and targeted, focused optimizations are applied to the tagged loops. Okay, a little bit about motivation. So MLIR IR or MLIR Python bindings are very verbose, and it is a compiler front-end output not meant for language users to write. And also Python is popular in the AI scientific community. So the requirements for PyDSL is that it should be directly usable from Python, adhere to default Python syntax as much as possible. So ideally, user can take their existing Python code with very minimal changes and run on PyDSL. And it facilitates heterogeneous code generation. Part 1 of the talk was given at the end of last year. That's the video and the slides. And the PyDSL parses a program, generates the transform dialect IR and the affine kernel IR, goes through the optimizer and lowers down to either Kunpeng or Ascend backend. This is the IR if you have to write it by hand. Extremely verbose, and just comparing the lines of code is about 3x productivity boost in terms of lines of code. We benefited a lot by inspiration of external projects, including MLIR Python extras, which improved usability of Python binding, XDSL, which is complete MLIR written in Python, as well as a very lightweight PyMLIR to parse and output MLIR if you don't want to build a whole LLVM project and want to just manipulate the MLIR. So here is an overview of PyDSL. It supports multiple MLIR dialects, arrays, SCF, func, memrev, affine transform. This bullet point on the is a little bit backwards, but what he meant to say is a Pythonic syntax of A plus B will output an arrays add op of A plus B. And it supports compiling and calling the function directly through NumPy arrays. On the right, there is an example where you can create a NumPy array and just pass the array into hello memrev, and it does some computation and spits out a NumPy array, and you can print it out. So for the talk today, I'll just focus on features that were developed since end of last year, which is type inference, as well as the macro system. So type inference are symbols, dimension, affine maps, and all these inference. Here it goes to a little bit of an example. So because we have to generate the PyDSL has to literally spit out MLIR, and MLIR is, you need all the type information in there, so it's a static typing. But if you have to write type hinting everywhere, it's a little bit laborious. So we are able to infer the types of, we create this number type wrapper. For example, for constants 12, it's being operated on with argument A, which is a UN64. Therefore, 12 will become an I64 type. So there is a little bit of help for the user. And last year, we presented how we write an affine for loops and how explicit we had to spell out whether it's a symbol or a dimension or AM affine map. That's very laborious, and we have since then been able to infer that, and the code on the right is now much cleaner. And we also added support to affine if using integer sets, and we hope to contribute that to upstream. Okay. Now we are at the key part of the talk, which is the macro systems. So the macro system, the name is because we are actually getting a part of the AST node, and we had to spit out the corresponding MLIR. So it's a little bit like a macro expansion, you can think of it like that. It's designed for extensibility and modularity, and it's being extensively used in the latest PyDSL to refactor the code. So how does it work? So on the lower bottom, you see a Python AST that's being generated via the AST module. That's an example from part 1 of the talk. And there are a lot of nodes there, and most of the nodes are pretty simple and basic Python, come from Python syntax, such as when you hit a function def, you should generate a func op. When you hit some constants, you should generate constant ops, and if you hit a add, you should generate an add op. These are pretty straightforward. So when we use the AST node visitor visits through these are pretty simple. So they can be well processed by our MLIR2 MLIR visitor, which is indicated in an orange smile. So that's there. So you will process that. However, not everything is as simple. In the code there, you will very soon hit a more complex op called a for, or a tag, which is for tagging loops with a unit attribute. So these ops are, these AST nodes are more complex. Why is for complex? Because depends on the range, it behaves differently. If the range is an affine range, then you need to generate affine for. If it's SCF range, you generate SCF for. So this job is a little bit too complicated for the main visitor to handle. So it delegates that job to the blue smile, its good buddy. It's the iterator macro. In this case, this example is an SCF range iterator macro, but it may as well be an affine range macro. This macro knows exactly how to process this for op, including how do I get the upper bound, lower bound, and all the good stuff related to the for ops. Similarly, the tag, you will call a call macro to process that AST node. So as I said, the visitor is happily chugging along the tree, and there it comes to the for op. So the for node on the AST. There, what it does is it passes itself, the visitor itself, as well as the entire subtree of the for circle in blue to the range iterator macro. So therefore, it says, well, I'm not going to process this part of the subtree. Let's give it to my friend, which is the iterator macro. It will process it. And it knows it needs to generate an SCF for op from the MLIR Python binding. So it goes about doing that, checks that the iterator is not a tuple, some simple checking, and also creates a block. And this part gets interesting. So the iterator macro comes to process the body of the for loop, and it says to itself, this is not my job again, because processing the body of the for loop are regular Python, basic common Python code. That's the job of the main visitor. Conveniently, the main visitor passes itself into the onFor. So now the macro can say, let's pass the job back to my friend, which is the main visitor. So it on the bottom right hand, you can see that it invokes the visitor to visit all the nodes. Okay, so that's the part that I just talked about. So it delegates the work back to the main visitor. So there is a little bit of back and forth going on. Just to recap, what's a macro system where the main visitor starts processing, generating MLIR, and then passes it to the iterator macro, and which passes it for the body of the for loops, passes it back to the orange smile, which is the main visitor, and the iterator macro returns and back to the main visitor. So there is a double delegation going on here. So I guess just to drive the point home, why do we need macro system is to let the main visitor able to extend for new features. That means the main visitor covers basic Python syntax and macro covers all the domain-specific stuff. So you can have a metaphor in your brain that PyDSL dialect macros are specific custom operations where the expansions are these passes, such as the onFor, to specially process them. Alrighty, so we just refreshed the whole PyDSL REPL yesterday, so you can go have a try on the website. That's it.